I'm from the SP Group, which is the utility company here in Singapore. And as every one of you know, the AI and machine learning is revolutionizing every industry. There's no exception. The same for the utility industry. So we start to think about how we can utilize the data assets we have to provide the intelligent services for our customer. So actually, for this industry, from my personal understanding, we have two problems: consumer machine learning and the industrial machine learning. For the consumer, we want to provide the more energy insights to consumer to help them to improve their energy efficiency. For the industrial side, we have our grid, our network, our assets to manage. We want to use the data to improve our operation and improve our management of the assets. And also we have an energy problem because more and more renewable energy, like the solar panel, like the battery, how do you manage all these resources using the data? So we have different kind of problem to solve, but in this session, I will talk about one specific problem, how we analyze the electricity data for energy monitoring problem. So let me start with the introduction. So the electricity is the fundamental part in our life because it drives all the activity in our modern society. In Singapore context, we have around 1.4 million retail accounts, including residential households, commercial and industrial customers. And the electricity consumption has rose to 48 terawatt hour in 2015. Then so now 2017, I think it even increased. And if you realize your mobile phone or your internet access somehow capture the people's digital life, the electricity or energy consumption actually captures some information about people's physical life. So for the household, it means what kind of equipment, what kind of appliance you use, and your lifestyle. For the commercial, like the restaurant, the shop, the factory, it means what kind of activity you have in your daily business and what's your productivity. So it's kept very unique data complementary to the traditional, the consumer transaction data you will see from the internet company. So with the deployment of the smart meter, we start to collect more and more data about the electricity consumption. So right now, for non-contestable customer, your meter is read every 2 months by meter readers for billing purpose. So you got 6 readings per year for every single customer. With the smart meters, more and more customers will have their meter sending out the readings every half an hour. So you got 48 readings per day, about 17,000 readings per year for customers. And in the future, the meter can even provide close to real-time readings. For example, like every 10 seconds per readings. So you got around 7,000 readings a day and more than 3 million readings a year for every single customer. So you can see the data dramatically increase for this IoT data. And all these meters were sent through the advanced meter infrastructure. We call it the AMI. So the smart meter on every premise will generate the readings and send to the data collector through the local mesh network. And the readings is then aggregated and sent back to the meter data management system through different communication channels. So with more and more data about the electricity consumption are captured, so we start to think about how we can utilize this data to help our customer to make their life better. Specifically, we will focus on 2 applications. The appliance detection to detect whether a target appliance is used or not, and the anomaly detection to detect the unusual energy usage. So why we do this energy monitoring? Because it can help customer in different aspects. First, it's about the safety and security. Monitoring your energy to ensure the safety of your family. Second, it's about the cost saving. So using the energy monitoring to identify the opportunity for energy efficiency to reduce the energy waste. Last but not least, it will help to understand the people's physical life and help the people to become more healthy or more productive. Here are some potential use cases. An example for safety, if your iron is turned on when the parents is not at home, you want to be alert to take action to make sure the safety of your kids. An example about the cost saving. If you forget to switch off your aircon when you get up in the morning, you want to be alert immediately to turn it off before you leave home. Instead of when you come back home at night, you suddenly realize your aircon is turned on for the whole day, right? An example for behavior, you may want to know how long your kids play games or watch TVs. These insights will help the family to achieve a better lifestyle. So we want to analyze the electricity data for energy monitoring application. Let's see what's the challenge and what's our idea to attack this problem. To understand the challenge, we need to first take a look at how we capture the electricity data. Because right now, the smart meter is not deployed to every single household. We have some portion of the smart meter deployed for the commercial industry customers, but for household, it's in progress. So we need to use some other devices to capture the electricity data. Different resolution of the data can be captured in different ways. Some are intrusive and some are non-intrusive. So the non-intrusive sensor is preferred because the installation of the sensor will be easier and safer. So in our case, we use the CT sensor clamping on the power line to capture the electricity current data. Let me show you one example. This is the three-phase electricity current data for an office environment. So during the midnight, you can see there's not much usage, but you can see some always-on devices is turned on, and they have some very unique consumption pattern. Starting from the morning, 7:30, there are some staff arriving to the office. So they switch on the light, they start to use their computer to start to work. During the lunchtime, the usage has more variety because there are different activity happening in the pantry or breakout area. Some staff eating lunch there, playing the games, whatever. After 6 p.m. in the afternoon, you can see the usage start to drop because the staff start to leaving the office and reduce to minimum after 8 p.m. So you can see there are rich time-related information in the data, which may be useful for other applications. With the example, I want to highlight three characteristics about the energy data. First, it's about the volume of the data. Once the sensor is deployed, the data will be captured continuously and keep growing. Second, all these data are time series. Every data point has a timestamp, and the time is actually a very important information for this type of data. Last, we may not have enough label for the data in most of the time because it's very expensive or difficult to ask the user to indicate what has happened at different times. This is also true for some of our machine data, for example, our sensor on the equipment. The reason why we cannot get a label is we have operation staff doing the maintenance and schedule and facing different events, but the operation data is actually captured in a hard copy. We haven't digitized a lot of historical data. So whenever we try to solve a problem, we ask the operation guys, can you provide me some labels? They say, yes, it's in some hard copy, please find it and figure your way to digitize it. So these three attributes actually bring up the challenge. So if we directly apply the traditional machine learning on the problem, we won't get the satisfied results because the label data is very limited. And on the flip side, we have a large volume of the raw unlabeled data. So we need an effective way to utilize the data to extract the useful knowledge for different applications. So that's the problem we try to solve. And we think about this problem, so we bring one idea to solve this. Our idea to attack this challenge is to learn useful features from unlabeled data and transfer the knowledge to the target problem. The self-taught feature learning will derive the time-related label from the raw time series data and learn the model to predict these time-related labels. By this way, we learn the useful knowledge from raw unlabeled time series. Once we learn this model, the useful knowledge is transferred to the target problem in the form of feature extractor. For the target problem, feature extractor can be used to transform the data to a better representation to solve the target problem. So this is a basic idea. Let's go into the detail on how we do this self-taught feature learning. The key idea under this self-taught feature learning is to form a supervised learning from the unlabeled data by using the time information. Given the fixed length time series windows, the first thing we do is we will derive a time slot labels from the timestamp information. Combining the raw data and the time slot labels, supervised learning will be trained to learn the model to predict these time slot labels. Once the model is trained, a feature extractor will be created from the model to transfer the knowledge to the target problem. Let's see the first step. The first step is to define the time label from the time. You actually have a multiple way to do it. If you have a prior knowledge about your environment, you can base on prior knowledge to define your timestamp. If you don't have enough or a strong prior knowledge, you can define the timestamp based on just the time period. Let me use the office data as an example. We have some knowledge about the office environment. We know normally from the 9 p.m. to 7 a.m. it's a non-working hour. They won't have too much usage in this period. So we define this non-working hour period as one time slot. And for the working hour, actually we don't have too much knowledge what it will be. So that's simply divided every 2 hours into a one time slot. So we chop the 24 hours of a day into different categories, different time slots. The second step is to learn a model to predict this time slot label. And this is the neural net we use. The three-phase current data is the input. You will go through a fully connected layer as a form of embedding. The core part of this neural net is a bidirectional recurrent neural net. We use the RNN because we want to model the sequential information of these time series windows. The last output of RNN will go through the fully connected layer and the softmax layer for classification. You see, this is a pretty standard architecture for kind of time series data formulation. But I will show you later, this kind of structure is already good enough to extract the useful knowledge for different applications. So my data scientists always, they will explore the new, more advanced components to put into this structure. But in this talk, I will highlight using this standard architecture, how we can achieve, how we can have on different applications. Time slot prediction itself may not be an easy task. So here, this is the confusion matrix of a model trained on the office data. You can see for some time slot, the prediction is quite accurate because, for example, like the midnight or early in the morning, because the usage pattern is quite unique. However, for some other time slot, the prediction is not so accurate because the usage pattern, for example, in the office, the usage pattern in the morning, it actually doesn't have too many difference with the usage pattern in the afternoon, right? So, but what I want to highlight, the time slot prediction model is not necessary to be perfect to extract the useful knowledge. Even for the time slot you can't predict where, the model will try to figure out, instead of randomly assign it to any time slot, you will assign it to the most similar time slot. This still, the useful knowledge can be learned and can be used for other applications. Once the model is learned, the network will capture the useful knowledge from the raw time series. And then we use the output of a last connected, fully connected layer as the feature extractor. Given a fixed length time series, we can pass it through the network to obtain the length features and use it as the new representation for the target problem. So this is the way how we use this network to another problem. Let's see what kind of knowledge has been learned from this self-taught feature learning framework. So here I show you the Disney projection of a new day of office data. So the left side, you can see the Disney projection of the raw signals. And the right side, you can see the Disney projection of the length features using the neural net I showed you just now. You can see the raw features of the data from different time slots are actually overlap with each other. And there are a lot of nonlinear structures. However, the length features of the data from different time slots actually separate the data from different time slots much better. And the nonlinear structure disappear. Instead, there are quite a lot of close to linear structure appear. If we zoom into some specific area, you can see the original overlap data from multiple time slots. After we project into the feature space, it was separate into multiple groups. And each of the different structure, there are multiple structure from the same time slot appear. If I show you the examples from the multiple linear structure in the same time slot, you can see the model learn to group the windows with the similar temporal shape. This is because the recurrent neural net, it tried to learn the sequential information. And also the model tried to be able to handle the temporal shifting. So the different windows with the same data, but just by temporal shifting, is drawn close to each other and form a kind of linear structures. Okay, so I hope everyone get the idea about how this thing works. So I don't just show you the neural network, but I basically show you what kind of thing it has learned from this network. Now let's talk about the application. So we have used this proposed framework on two different energy monitoring applications. The first one is the appliance detection using the supervised learning. The task is to detect whether a target appliance is used or not. Here is one example. So in the office environment, we want to detect whether a coffee machine is used by staff or not. The left figure shows the coffee machine, and the right figure shows you a sample of its load profile. The training data consists of a collection of the time series windows. For some of the windows, the coffee machine is on, and for some other windows, the coffee machine is off. We use the principal component analysis to visualize the time series in 2 dimensions. With the self-taught feature extractor, we can pass the time series window to the network and obtain its length features as the new representation. So similarly, we use the PCA to project the data into the 2D space. When you compare the PCA projection of the original signals and the length features, you see the similar effects. You see the appliance on windows are grouped together and has a less overlap with the appliance off windows. It is because the length features try to provide a better representation to differentiate different temporal shape. And this actually will help you to detect the appliance. So instead of using the law features, we use the length features to represent the data and then how to detect the appliance. So the linear SVM is used to classify the length features for appliance detection. The reason we use the SVM, because you can see just now for the self-taught feature learning, it's a deep learning problem because I have huge volume of the data. But for the appliance detection, actually it's not a deep learning because it's a traditional machine learning because I have a very small data set. There's a consideration around this about the application. When we want user to be able to use this function with a minimum efforts. So the numbers we require him to indicate us the Windows or the appliance on Windows will be very small. So the SVM is used because it provides a good generalization capability for smaller data set due to its max margin formulation. And we choose the linear kernel is because we observe some close to linear structure in our length features. But we use this classifier, it doesn't mean it's only limited to this classifier. Actually, you can use whatever classifier you believe it works. The length feature can be used in any classifier. So here I show you the detection results. We actually done quite a number of the testing to understand the behavior of the self-taught feature learning. We have few insights I want to share with you. First, we found in general, using the length features achieve better detection accuracy compared to using the law features. You can see it from the left figure. And this actually shows we actually learn some useful knowledge from the unlabeled data. Second, we found that knowledge we learn actually comes from the time information. How do we prove this? If you look at the red line in the right figure, that is the performance we get when we randomly assign the time slot labels to the windows. So we kind of do an experiment, like say, if I give you the wrong time information, how will you learn? And the performance actually is worse than the law features. So it shows that if the time information is wrong, no useful knowledge can be learned. That's the second insight I want to share with you. So actually it shows that the knowledge comes from the time information. So if you handle any problem about the time series, you really need to think about whether time contains important information for your problem. Then you need to look at that from that angle. And the third insight I want to share with you is like, if you look at the best performance we achieve, the two lines, is two models we train from 30 seconds windows and the model we train from the 5 minutes windows. So it shows a very interesting effect, means that we can train from the unlabeled data using whatever window size we believe in general. And then we can apply to the problem where the window size is different. So in our appliance detection, our window size is actually 1 minute. So this is an advantage when we use the recurrent neural net, because it's a sequential model. You don't need to care about the length of your sequence. So if you look at the original RNN is used for natural language processing, your sentence actually has a variance length. So similarly, for our windows, we have a variance length of windows. But you don't need to learn multiple models. You learn models for one window length, then you can apply to another window length. And another thing you observe is that two models actually achieve quite consistent performance, and which is much higher than the law features. This shows that the framework is actually quite robust. You don't need to rely on a specific setup to make this framework work. So different data scientists actually, they can tune different parameters, but in general, you can achieve the performance gain through this solution. We also apply this solution to another energy monitoring problem, anomaly detection. So it's another type of the application using the unsupervised learning. The idea originally was motivated by the supervised learning, but it can be applied on unsupervised learning as well. Our anomaly detection solution is based on the autoencoder. Autoencoder is a type of a neural net which uses unsupervised learning. So it consists of two parts, the encoder and decoder. What the encoder did is it tried to compress the original signal into some low-dimensional representation. The decoder will try to reconstruct the signal from the low-dimension representation. And the goal for this network is try to train the network to best reconstruct the original signal. So whatever signal you input into the network, you will try to generate the same signals as close as possible to the original signals. So when you apply the autoencoder to the anomaly detection problem, normally your anomaly score will be defined by the reconstruction error between the original signal and the reconstruct signals. So I show you one example is the anomaly score we use, which is the normalized reconstruction error. So we try to draw the score from 0 to 1. So similar to the appliance detection, we extract the length features by passing the unlabeled data to the self-taught feature learning to obtain the length features. The autoencoder is trained on the length features instead of the raw signals. Given the new data points, the autoencoder will compute the anomaly score by using their length features. By this way, the length feature will provide a better representation for the data to attack this challenge. You know, the challenge for the anomaly detection using the autoencoder is how do you control the complexity of a model? You want the model to be encode the normal data where, but not for the unusual data. You don't want it to be able to encode everything. Then you cannot detect the anomaly. So we believe the length feature from the self-taught feature learning can provide a better representation to help on this challenge. So our solution, instead of building a single autoencoder, actually we build multiple autoencoders for different time period. So for each time slot, we train one autoencoder by using only the time series window belong to this time period. There's a consideration around this design because there are multiple different structures in our time series, electricity time series. So building different models for different periods allow each model to focus on a smaller subset of the data, and which will help us to control the model complexity better. So how it works is that now you deploy the kind of system, every time series window you receive from the streaming, you know what period it belongs to. Suppose this is the window of 3 p.m., so now you pass it to the autoencoder for this time slot, it will give you the anomaly score. It will tell you this is the normal usage or it's unusual usage. We have implemented this anomaly detection system and deploy into our office environment. So along the talk, I will use the office data as an example to demonstrate you how everything is worked. I will show you 2 examples of the real-life anomaly examples. The first case happened on a specific Saturday night. Normally, there's no much usage at night in the office environment. However, on this specific day, somebody came into the office after 10 p.m. He switched on the light and used his equipment. He left after midnight. So you can see the consumption pattern in the top figure. From the bottom figure, you can see the anomaly score from the lens features, which is the red line, actually clearly indicate these unusual events. While the anomaly score from the low signals fail to do this. So we actually ask ourselves why using the low signals fail in this case. Because this case seems like quite easy. But we did some study, so our understanding is like this. So you have anomaly usage in this case. You have also the normal usage. The low signals of anomaly usage, however, is overlapped with the normal usage. So when your autoencoder is trained to encode the normal usage, it accidentally learns how to encode this abnormal usage as well. So that's why in the anomaly detection framework, representation of the data is a key. You need a good representation. So our lens feature actually learn how to separate different usage much better than the raw signals. So the first example of anomaly is about a usual usage occur in the time it shouldn't occur. So the second example of the anomaly I want to show you is a totally new unusual usage which never happened before. So this is an example. Some of our staff use a new equipment in the office environment during the working hour. So from the top figure, you can see there's some unusual usage happening at the beginning. And from the bottom figure, you can see again the anomaly score based on the lens features clearly indicate this unusual usage. And while it achieves a very low score for the normal usage during the other times. So this shows you some kind of example how the lens feature is useful for this anomaly detection problem. So last, let me briefly talk about the system architecture. So we try to implement the self-taught feature learning framework and also the downstream application into the whole system which we want to deploy into the production. The idea is we have on-premise and the cloud implementation. We want our implementation could be easily deployed on-premise as well on different cloud platforms. So the Kafka message bus is used for ingestion, also the online prediction, as well as the notification. So once the data is ingested, we have our on-premise infrastructure to train different models. The train model will be deployed to the model serving engine. And we implement the system in a way, the model serving engine, also the online prediction and notification publishing framework is able to be easily deployed into the Google Cloud platform. That's the experiment we do. So we want to be able to deploy this kind of system into any kind of cloud services and serve different customers. So for example, if there's a building or there's a factory, they want this kind of anomaly detection solution, we want to use the cloud infrastructure to serve this kind of customer. I think I will close the session by a quick summary. So we propose a new way, a self-taught methods to train the neural network to learn useful features from the raw time series by using the time information. And we have shown the learn features is useful for different applications. We showcase 2 applications, but I generally believe it is useful for any kind of information you need the electricity time series data. So that's all for my presentation. Thank you. Questions? Yes.
Can you suggest how we can tell if the key knowledge is from the time?
Okay, so just now I highlighted the point. So actually we asked the question whether the knowledge we check is from the time. So that's why, let me show you back there. Okay, so that's why in the right figure, if you look at the red line is actually the performance when we train a model by surprising the raw time series window with the label. However, this time the label is not derived from the timestamp. We randomly assign the label. Means we give it the wrong time information. So you see the performance of this red line is even worse than the raw signals, right? So from the other side, you will know why the other model trained based on the correct time slot labels achieve the performance gain is because of their some time information exists. So that's the way how we prove it. Because it's a tough problem. We can't directly prove it. So instead of that, we say, okay, instead, suppose I don't provide you the right time information. If the performance drop, then on the other side means that the performance I achieve is coming from the time information. That's the only way we can try to observe right now. Yes. Yeah, actually we did. So we actually do a lot of different variants of the neural net. So suppose my last piece is not single fully connected layer. Suppose I have a MLP, I have multiple layers. So we can try on different layer. I can even take the output from the RNN directly. So we try that. So in general, there's some difference, but not so much difference. Means in general, the output from different layers achieve somehow the improvement. Some is big, some is small, but it's not dramatic difference. So that's why we highlight the most simple architecture. But for the specific problem, you actually need to try on what is the best neural net architecture for you to achieve. Any question? Yes?
Since there's some time dependency, was LSTM ever considered?
No, actually we use the LSTM. I mentioned we use the RNN, but I'm not using the LSTM. I use the gated recurrent unit, GRU. So it's similar to LSTM.
Why did you go to the bidirectional
Yeah, so because in our problem setup, we are given the fixed length of a window. So this is not like the time series forecast. So it's like the time series classification. So we can utilize the information from 2 directions. So that's why we initially want to use the bidirectional. But you are right, you can simplify it to using just a normal LSTM or GRU, and I believe you will achieve a similar performance.
The time slot method, do you think have any limitations?
I think there's some limitation. So it depends on the problem you are looking at. So if in your problem, if you believe the time, there's a temporal pattern on different times, then the time slot in general, it will work. But if your problem, you found there's no much information about the temporal, means the data actually cannot be grouped on the different time slot, then the effect of it may be less. We actually tried that something in our setup is like, instead of doing like the working hour and the non-working hour, we just simply group every half an hour as a time slot. So you can imagine this is the extreme case. We don't have any prior knowledge about the environment. So we just simply say, okay, based on a proximity in the time axis, I just want to group the data point close to in the temporal domain. The performance of this kind of time slot is in between. So it still has the better performance than the raw signals, but it's not as good as the time slot we define for the office environment. Because the office environment, you have very clear knowledge, right? The non-working hour, you don't have too much usage. So the knowledge or definition in the time slot, which actually will affect the performance, the improvement you gain, depend on your problem.
So the case you give first is about repetitive cycles. How about trending? Time series and trending.
Can you more specific about the application?
Office is Monday to Friday, right? But let's say it's have a scroll inside of trending inside of cycles. So trending means you have a tendency to grow every day by day.
Right.
So,
like the seasoning effect kind of thing, right? It's on the year. So, but what's your target problem? You want to forecast or you want to? Okay. So if you say your pattern only appear in this kind of trending, means it's more like long term, it's not a repeating cycle, then I guess you need, more data to make it work, because there's no this kind of repeating cycle, right? So it means your data actually need to contain enough, pattern inside the trending. So your time slot, instead of like within the day time slot, your time slot may be longer. Maybe it's like the season or what. Then you can apply this framework to explore the time information for your problem. Okay. If there's no any other questions, okay. Yes. Yeah. So we actually, in our office environment, we build two models. So our time slot for this is only apply on the weekday, because the weekend is totally different. Yeah. So we have different model for that. Exactly. Okay. So thanks for joining the session. Hopefully you enjoy this. Yeah. Enjoy the rest of the conference.